about to start. So today we're pleased to have Donnie from LTI. He's one of Noah Smith's students, and he's going to talk to us about time-dependent model parameters.
Thank you. Thanks all for coming. So this is joint work with my advisor Noah Smith, and on some parts of the talk are also with several other members in my research group. Okay, so when we collect data, we usually have the timestamp of the data, either when we get the data or whether when it was generated. But common approaches in machine learning usually ignore the temporal dimension of the data. So we usually just proceed as if they are IID samples from some distribution and learn a model. So we believe that for some tasks, especially for predicting the future, it's not the best approach. We can actually do better if we take into account the temporal dimension of our data set. Okay, so that's what we're going to do in this work. So we're going to incorporate temporal dimension of the data into a machine learning model. So here's a small example I have. So suppose that every year, since 2004 until 2012, we collected data. So that's like 8 years, or 9 years, okay. So we have data every year, and we want to make a prediction about something that's going to happen next year today. Okay, so the first question that we should ask is how much data we're going to use. So of course we can use the entire data set, because more data always usually means better model for standard tasks. But we can also argue that it's actually better to just use the last year of our training data, because it's more recent and probably more relevant to the prediction that we're going to make. So whereas data from 10 years ago, for example, probably are just not relevant at all. Okay, so here's one task, just like an example task. Suppose that we're trying to predict whether a paper will be cited or not 3 years from its publication. So we can see that for this task, we actually get better result, higher accuracy using the entire data set. So that's what all years mean. So we get about 70% accuracy. Whereas if we just use papers from the previous year, we get about 67%. But here's another task. Okay, so in this task, we're doing regression. And we're trying to predict the volatility of a stock 12 months from today, for example. And in this task, we can see that it's actually better if we just use training examples from the previous year as opposed to the entire data set. The entire data set is about 10 years or something like that. So we see here that it's a very task-dependent choice. And I'm only showing you like last year or the entire data set. And there's always like 2 years, 3 years, 4 years, and so on. So in this work, we're trying to build a model that tries to learn that during learning, such that it actually picks the best time horizon for training your data. Okay, so this is the outline of my talk today. I'll start with a review of generalized linear models, because that's the class of models that we're going to use. And then I will present our first attempt of building a time series model, show some results, and then I'll show another approach, and then show another set of results before concluding the talk. Okay. So here's what linear models look like. So our output is a linear function of feature factor x and a parameter factor beta. So this is just standard linear model, and training using empirical risk minimization is just minimizing this objective function, where we have a loss function here, L, and usually we also have a regularization function, R. Okay, so here's a couple examples of loss functions that can be used. So if we want to do linear regression, we can use the squared loss. And if we want to do logistic regression, we can use log loss. There's also several choices of regularization. This is not all I just showed you for. There's a lot more. But so a few common ones in ridge regression, for example, you penalize your feature factor by the squared L2 norm of your feature weights. For lasso, you penalize it using the L1, and there's this thing called group lasso and fuse lasso, and a few others. Okay, so what we're going to do is we're going to propose a new regularization function that incorporates temporal dimension of the data into our model. Okay, so this is what we're going to modify in the GLM's framework. So we're going to keep the loss function and modify the regularization penalty. Okay, so here's our first time series regularizer. So the way it works is that for every feature in our data set, we make copies. So first we need to divide the data into discrete time steps. Okay, that's the first thing we need to do. So for example, here we have yearly time steps for 5 years. Okay, and then for each feature, you make a copy of that feature for each time step. So originally we have just like one feature language. Now we have 5 each of language. So this, for example, 2006 language only fires in 2006. 2007 language only fires in 2007, and so on when we're training the model. So I will just show you what the regularization function looks like first, and then talk about the probabilistic interpretation of that afterwards. Okay, so this is our proposed regularizer. So it consists of 2 terms. So the first term is just a standard ridge penalty, and the second term promotes smoothness in changes across time. So we penalize it by the squared difference. So it's going to be a smooth change over time. And this is just for, so for example, the intuition is that the feature weight for language in 2007 should be close to the weight in 2007 and 2005. That's the intuition. So that's our penalty. And since we penalize it by the squared difference, we encourage smooth changes across time. Okay, so it has 2 hyperparameters, lambda and alpha. I would like to say a few things about alpha here. So if we set alpha to 0, we basically just train independent ridge regression for every time step because the second term will go away. And if we set alpha to a very high value in the limit, we will just get a single feature weight for the entire copies of features we have, because the second term will be very high if they are not the same. So in the limit, it's just the same as having one big ridge regression for your entire data set, and you don't make copies, and you just ignore the temporal dimension of the data. Okay, so most regularization functions come with a probabilistic interpretation. So for example, this is a few common ones. In ridge regression, we know that we can assume that the feature weights that we get are draws from 0 mean normal distribution with variance parameterized by lambda. And for lasso regression, you can assume that they are generated from a double exponential distribution or Laplace distribution. Okay, so our time series regularizer also has well-defined probabilistic interpretation. So in this case, we can assume that every feature weight, so for a single feature over time, the feature weights are drawn from a multivariate normal distribution with 0 mean, and this precision matrix here. Precision matrix here. So this is for a single feature over time. Okay, so for a feature language, so the size of the matrix is t by t, where t is the number of your time steps. And you just draw once from this multivariate normal distribution for your feature weights over time. Okay, so that's the probabilistic interpretation of our regularization. We can also draw a graphical model for our model. So axes here are observed feature values, y's are the response variables, and alpha and lambda are fixed priors. So the first order dependencies here correspond to the off-diagonal entries in our previous precision matrix. And for those of you familiar with time series literature, it actually has a very close connection to a first order autoregressive process, except that we are doing it for latent variables. So usually you observe what the value are in previous time steps in AR process, but here they are latent variables that we need to infer. Okay, so that's our first regularization penalty. Okay, let's try it on a couple tasks here. So the task here is to predict the feature impact of papers at the time of its publication. We define impact by the number of downloads and the number of citations that a paper will receive in the next fixed period of years. So okay, it's not really impact, but we think it is highly indicative of how impactful a paper is. And since this is what we can get, right, because you cannot really measure impact. So for this task, we have a couple of data sets. The first one is about 9,000 economics papers from the National Bureau of Economics Research. So we have papers from 1999 until 2010, so that's about 11 years, and download logs. And the second data set we have is from the ACL corpus, so this is computational linguistics papers for about 28 years, but we're actually only using 26 years, until 2006. I need to fix that. Okay. Just to give an idea of the response variables that we're trying to predict, so on the left are log number of downloads. I'm sorry. And so they look pretty close to a normal distribution in the log space. And on the right, it's the number of citations. But it's very different. 50% of the papers aren't even cited at all within 3 years after publications. It's kind of sad, but okay, we decided we're going to do classification for the ACL corpus, and we're just going to predict the actual number of downloads for the NBR dataset, because this is like boring, right? I mean, okay, well, most of them will be 0. We need to cite more papers. Okay, so these are the features that we're using. We use just pretty standard features. For the tags, we use simple unigrams, bigrams, and trigrams. Yeah, just binary indicator features. And for we also include some metadata features such as the author names and publication venues. So this is the result for the first data set. The size of the test data is about 1,000 papers. This is mean absolute error. Median is just if we predict the number of downloads as the median of the downloads counts in our training data. So it's just like a single value for every paper. Last year is ridge regression trained only on the previous year. And all years are ridge regression trained on the entire data set. And time series are, of course, our model. And we can see that we do better than competing models, and the improvement is significant. And so this is for the second data set, different task classification here. So what the numbers I'm showing you are classification accuracy, so higher is better. And basically similar story, models that are that take into account temporal dimension of data, which is our model, did better in this task. Okay. So just to give an idea of like what are learned by these competing models. So these are two diagrams, unemployment rate and inflation rate from the NBER dataset. The y-axis is the feature weights learned by the model, and the x-axis is time. So if we just train a single big regression model for the entire dataset, what we will get are the blue lines. So of course, we will just have a single value, right, over time. This is like the value that you should use. If we train independent ridge regression every year, what you will get is something very bumpy. So that is the red lines over here. And if we train our model using our regularization function, you get something smooth, which is the green lines in the plots. OK, so we can use it to analyze trends. So this is the nice thing about our regularization penalty. So, but trends, why don't you just use frequencies, right? I mean, they are also trends. So this is for ACL corpus. You can get trends by terms frequency. So the y-axis is the proportion of the n-gram that is that particular n-gram. So this is the colors for those lines there. Okay. So this is what you will get using term frequencies. But this is what you will get using by analyzing the feature weights learned by our model. So they are very different. For example, we can see machine translation here. Machine translation is the pink line. So that one. It's actually going down in terms of frequencies over time, probably because the field is getting more diverse these days. So we have a lot of different terms. But as the feature weights for machine translation actually goes up, meaning that it gets more popular. So all things being fixed, the presence of the bigram machine translation gives you a higher probability of being cited. Of course, if you fix all things, which it's not like you can just write empty, 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 and then your paper will be cited. OK, so that's the feature weights learned by our model. OK, so this was a paper at EMNLP last year. So from this point forward, it's actually, we're still preparing the paper for submission. So comments are welcome if you have any comments from this part of the talk until the end. So OK, that regularization that we propose is nice. We think it gets good results, and it gives something more than just frequency trends. But it still has some limitations. So first, it doesn't encourage feature level sparsity. So when I say original feature level, we make copies of features for each time step, right? But we penalize them separately, independently. There is nothing that says that, oh, OK, if one of them, like, you all should go to 0 together, or maybe you should not, something like that, because we make copies. Of course, we have the smoothness penalty, but that's pretty much it that governs. Like, they don't like push everything towards 0 together. So that's one. The other one is that for every feature, it has to have the same correlation degree over time, because we have this alpha, and we need to turn it. Of course, if you are willing to turn 50,000 alphas or something, yes, you can have 50,000 different alphas, but that's just impractical. It's impossible to do. So that's another limitation of the model. So in order to overcome these limitations, we propose a different model. And in order to explain that, I need to say a few things about probabilistic interpretation of group lasso. So this is from a paper by Figueiredo at 2001. Somewhere, I don't remember, I'm sorry. But yeah, so we can interpret group lasso probabilistically as, so for each group, so this is for non-overlapping group lasso, okay, this is important. So you have non-overlapping group lasso, and for each group, you assume that you first draw a scalar from an exponential distribution. So that's sigma g there, and then for each feature in the group, you draw the feature weights from a normal distribution whose variance is parameterized by sigma g. Okay, so this is the probabilistic interpretation of group lasso. And he also proposed a different parameterization of the scalar multiplier distribution. So they showed that you can, instead of using exponential distribution, replace it with a Jeffreys prior. So this is what Jeffreys prior look like. Probability of sigma is proportional to 1 over sigma. Of course, this is improper and uninformative and so on. But they showed that you still get good results and still get sparsity. And more importantly, you don't need to have lambda anymore. So you don't need to tune a hyperparameter. So this eliminates the need of tuning one more hyperparameter. So that's group lasso. Okay, so let's modify our regularizer. Okay, so what we first are going to do is we group them together. Now we have a group, right? So for a feature, over time, we define them as one group. And our groups are also non-overlapping groups because they come from different parent feature, right? So for every parent feature, you have features at each time step, and then, of course, they are non-overlapping. Okay, so we assume that our feature weights now are generated by the following process. So similar to group lasso, we draw a scalar multiplier. So here I showed the Jeffreys prior version, but if you're willing to turn lambda, of course you can use the one with exponential distribution. And then for each feature weights in a group, you draw it from a normal distribution, but instead, so we have a precision matrix lambda here. So the only difference with group lasso is that instead of the identity matrix I, we use a precision matrix lambda. Okay. So what does this lambda look like? We propose the following lambda. So there is one lambda for each group. Okay, this can be different for every group. And we propose the following matrix. It's a tri-diagonal matrix with diagonal entries 1 and off-diagonal entries alpha. So we just assume that all the off-diagonal entries are alpha for one matrix. So it's just uniform tri-diagonal matrix. Remember that we also multiply this by sigma here, right? So we can just fix the diagonal entries to 1. Another thing we need to do is we need to make sure that it is a valid precision matrix. And actually, one can show that as long as alpha is between minus 0.5 and 0.5, your resulting matrix will be positive definite, so it will be a valid covariance matrix. Of course, this doesn't capture the entire support of precision matrix, but we believe that it is still flexible enough because, like, you can vary alpha, you can also vary sigma in like the one I had before, right? Okay, now we know that alpha needs to be between minus 0.5 and 0.5. So how do we encode this restriction to our model? We choose to put another prior on top of alpha and marginalize it out during inference. So we're going to use a truncated exponential distribution for the prior of alpha. And specifically, we're just using between -0.5 until 0 because we believe it will, we just want positive correlations between features at adjacent time steps. So remember, this is a precision matrix, right? So negative entries mean positive correlations given all other entries. But of course, there's nothing that prevents you from using a prior between 0.5 and 0. So this is what a truncated exponential distribution looks like. And it has one hyperparameter tau. OK, so that's what we're going to do with the precision matrix. We can show a graphical representation of the model. So here's what it looks like. Y are the response variables. X are the feature values. And this is how we generate the feature weights beta. So it has one alpha and one sigma for every group, but tau are a global fixed prior. And then during inference, we will marginalize sigma and alpha and maximize beta. So that's why it's doubly circled. But I will talk about inference actually now. OK, so that's like our model that we would like to have. Now the next thing we need to do is to define learning and inference procedure under this model. So in short, we're going to do variational EM. We are doing Bayesian inference for sigma and alpha, and we're going to maximize beta. So this is important. Unlike Bayesian regression, we don't marginalize out beta because it will be very hard. I think it's just messy, and usually this gets better results. So we're going to perform a affine point estimates for beta, but marginalize sigma and alpha during inference. I'm tired. OK, so this is the objective function that we're trying to maximize. This is actually the variational lower bound that we're trying to maximize. OK, so this is not the objective function. This is the variational bound that we're trying to maximize because we're using variational inference. It looks messy, but it basically consists of 3 components. The first one is your likelihood. So that's the negative loss function, your data likelihood, that one. And the second component is the likelihood under the generative story of feature weights that I just described before. So that's this part. And the last part of the bound is the entropies, because we're only maximizing the variational bound. So we're using variational distributions and minimizing KL divergence. So we just have entropies here. OK, so this is what we're trying to maximize. OK, so more specifically, we use fully factorized distributions in this step. So for each group, we need to update variational parameters for sigma. So for the variational distribution, we use gamma distribution. So it has two parameters A and B. And so we choose gamma distribution because we think it's flexible enough to capture at least unimodal distribution. So it's just an arbitrary, OK, not an arbitrary choice, but it's a non-conjugate relationship. But we just decided, OK, we're going to use gamma distribution because it looks flexible for a unimodal distribution. So that's for sigma. We need to update A and B, basically, in this step. For alpha, we choose truncated exponential distribution as our variational distribution. So this is the same as the prior, although actually it's not a conjugate relationship. But if you use variational inference, you can do all these kind of things, which is really nice, as long as you can take the gradient of your bound with respect to your variational parameters and compute the expectations under your variational distributions. So OK, we decided we're going to use gamma distribution and truncated exponential. This is the step, basically. And there are no closed form updates for A and kappa, so we do numerical optimization basically for every step. For B, there is a closed form update. And in the M step, we just do something very similar to when we train any kind of regression model. So just maximize over beta given a fixed estimates of our variational parameters. So this is just standard maximization. You can use any favorite optimization method. First order methods, LBFGS. We use LBFGS, but anything can be used here, basically, any optimization method. OK, so that's our second prior. Let's try it on a task. OK, so we're going to do a different task here. We're going to predict the volatility of stock returns. The volatility of stock returns, yes, from financial reports of the company. So volatility is defined as the standard deviation of a stock returns over a finite period of time. And we are going to predict 1 year after the report is published. So basically, every company has to publish a report every year. And then when they publish the report, we're trying to predict, based on this report, the volatility of the stock of that company a year after that report is published. So that's basically the task that we're going to do. So for this task, we have a data set of about 27,000 reports from 1996 to 2005. OK, so this is the data set that we're going to use. And this is the log volatility, the distribution of log volatility. So we can also see here it's pretty nice. It looks close to a normal distribution in the log space. So we're going to do regression here. And similarly, we're going to just use simple unigrams features from the reports and some metadata feature, which is the volatility of the stocks a year prior to the report. Because in economics literature, they've shown that this is a good indicator of the volatility of a company in the next year. So we include this as our metadata feature. So this is the results over about 13,000 test examples. The numbers are mean squared error in the log space. And the first thing I would like to show is this. We can see that our first time series model beats its ridge counterparts. Like so, it did better than the two ridge models. But specifically for this data set, lasso regression actually did a lot better. OK, we also ran lasso regression for the first task that I showed, but they performed similarly. OK. But our time series model basically beats all the other competing models significantly. OK, so this is nice because it shows that it captures a nice correlation degree for different features over time. That's one, and it requires less tuning actually, because now we only have one hyperparameter, which is tau, and the model is not really sensitive to tau actually in our experiments. OK, so that's the results. Just to conclude the talk, we presented two time series priors that incorporate temporal dimension of the data into the model. And we showed that our models beat models that ignore temporal dimension of the data on various real-world data sets, and the improvements are significant. OK, that's it. Thank you.